Hello everyone, welcome back to my channel Certainty of Physics. I hope you are doing great and are you ready for another exciting physics investigation? Before beginning it, can you close your eyes for 5 seconds? Can you hear something? Maybe a fan, maybe a vehicle outside, maybe someone calling your name. You can hear all these sounds, but can you actually see them? Can we touch it? Definitely your answer is no. If sound is invisible, then how does it travel from one place to another? Today we are going on a fascinating journey into the hidden world of sound. A world that surrounds us every second but remains completely invisible. Welcome to that invisible energy that is sound, unlocking the hidden physics of sound around us. Let us begin with a mystery. Suppose an astronaut is repairing a satellite in space. Suddenly a huge metal object crashes nearby. Will the astronauts hear the sound? Most people say yes, of course, but the answer is no. Now imagine standing in a concert hall with a loud music. You can hear every beat clearly. Then you may ask, why the difference? The secret lies in something called a medium. Sound needs particles, air particles, water particles, or maybe solid particles to carry its message. Space is almost empty, so there is no particle to pass the sound along. So without particles, there is silence, which is, as a teacher, we expect in the classroom. But the classroom is filled with air molecules or air particles, so the sound travels throughout the room and that reaches the teacher's ears. So everything is having a beginning. Every story has a beginning. Like that, here the sound is also beginning. Let me know how it begins. Think about plucking a guitar string. The string moves back and forth rapidly. Or think about speaking. Your vocal cord vibrates every time you talk. You can feel by touching it with your fingers. These vibrations disturb the nearby air particles. The particles bump into their neighbors and the disturbance starts spreading outward. Just like dropping a stone into water creates a ripple, vibration creates sound waves. So the real hero behind every sound is vibration. As we discussed in earlier, the sound needs medium. For that, we do a small simple experiment. Imagine you are standing in a swimming pool with a metal spoon in your hand. You gently tap two spoons together above the water. You can hear the sound clearly. Now, what if you tap the spoons underwater? Something surprising happens. The sound does not disappear. In fact, it can travel even better through water. But why? To understand this, let's remember one important point. That is nothing but sound needs a medium to travel. This medium can be a solid, liquid, or a gas. In air, the particles are spread far apart, so when sound travels, it loses energy more quickly and moves relatively slow. But in water, the particles are much closer together. They can pass the vibrations from one particle to next much more efficiently. That's why sound travels faster and further in water than air. And it is even more interesting In solids like metal or steel, particles are packed even more tightly. As a result, sound travels fastest through solids. So if you compare the speed of sound, faster in solids, faster in liquids, slower in gases. This is why the railway workers sometimes place their ears on track to detect an approaching train long before they can hear it through the air. The journey of the sound depends entirely on the medium it travels through, and the closer the particles, the faster the journey. Many people imagine sound as a thing moving through the air, but sound isn't an object. Sound is an energy being passed from one particle to another. For example, think of a line of dominoes. When the first domino falls, the energy travels through the line, even though each domino only moves a little. Similarly, air particle does not travel all the way from the speaker to your ears. They simply passes the energy forward. So, sound is not a matter moving, it is an energy traveling. Now, let us zoom in and see what happens inside a sound wave. When a vibrating object pushes air particles together, we get a region called compression. When particles spread apart, we get a rarefaction. Compression, rarefaction, compression, rarefaction. This repeating pattern travels through the air. Imagine a crowded train platform where people move closer together and then spread apart repeatedly. That's exactly how sound travels through the air. Let us get into the anatomy of a wave, making the invisible visible. Every wave has important parts. The highest point is called the crest. The lowest point is called the throw. The distance between two crests is called as the wavelength, or the distance between the two throws also called as wavelength. These measurements help scientists understand how sound behaves. Just like doctors study the human body, as the physics students we study the anatomy of wave. Previously we discussed that sound can be represented in a waveform. Now, let us imagine you are standing beside a calm lake. You are throwing a small stone into the water and beautiful ripple begins to spread out. Now, if a scientist were standing next to you, they wouldn't just admire the waves, they would start measuring them. But what exactly would they measure? To understand any wave, including sound waves, we need three important measurements. The first one is wavelength, which is represented by lambda. Think of wavelength as the length of one complete wave from one crest to next crest. It's like measuring the distance between two neighboring hills. Next, come to the time period. This is the time taken for one complete wave to be produced. Imagine using a stopwatch and measuring how long it takes for one full cycle of the wave. Now come to the most important one, which we call it as a frequency. It is that how many waves pass a point in 1 second. If only a few waves are passing every second, then the frequency is low. If many waves are passing every second, then the frequency is high. Remember, frequency is always measured in hertz. Here an interesting relationship. If we have taken a long time to complete, few waves are produced every second. If each wave is completed quickly, more waves are produced every second. That's why frequency is equal to inverse of T, or simply we can say F is equal to 1 by T. Now let us put everything together. Speed is equal to distance by time. Here the distance is nothing but wavelength into 1 by T. So this 1 by 2 is nothing but frequency, that is equal to lambda into F, or V is equal to F into lambda. This equation is like the master blueprint of the wave motion. If you have any two quantities, you can find the third one. Whether it's sound wave, water waves, or even light waves, this simple formula helps us understand how waves travel through the nature. So whenever you hear a sound, remember behind that sound is a hidden mathematical blueprint guiding its entire journey. Thank you. Have you ever seen lightning before hearing thunder? That's because light and sound travel at very different speeds. Light travels so fast that it reaches your eyes almost instantly. Sound is much slower, so after seeing lightning, count the seconds until you hear the thunder. If the gap is 5-second delay, means the lightning strikes exactly 1700 meters or 1.7 kilometer away from your location. That means nature is giving us a free distance calculation. Let us settle a race. Who wins, light or sound? So what type of wave it is? A light is electromagnetic wave, whereas our sound is a mechanical wave which needs medium. So the shape of the electromagnetic wave is transverse, whereas it is a longitudinal wave in the air. It can travel in a vacuum, whereas sound needs obviously the medium. So when the speed of the light is 3 into 10 to the power of 8 meter per second, whereas the sound needs 340 meter per second. So that's why during a thunderstorm you always see the lightning first and hear the thunder later. Light is one of the most fastest travelers in the universe, while the sound takes a much slower route. Have you ever shouted your name in an empty hall or near a mountain, or suddenly heard your own voice coming back? Hello, hello. It's almost feel like someone is repeating your word. But who is answering you? This answer is simple. It's your own sound coming back. Let us see how it is happen. When you speak, sound waves travel outward in all directions. As these waves move forward, they eventually hit an obstacle like a wall, a cliff, or the side of a building. Now the sound behaves very much like a ball hitting wall. Instead of stopping, the sound wave bounces back. This bouncing back of sound wave is called reflection of sound. But not all surface reflects sound equally. Imagine entering a room filled with thick curtains, carpets, and soft cushions. This soft material absorbs sound energy, so very little sound is reflected back. That's why such rooms feel quiet. On the other hand, hard surfaces like concrete walls, tunnels, mountains, and empty halls reflect sound strongly. They throw the sound back towards us, creating clear reflections. So every time you hear a reflection, remember that your voice traveled forward, hit a surface, bounced back, and returned to your ears. This like sound taking a round trip and telling you, I am back. Reflection of sound is nothing but when sound is produced by the source, it reaches any object, and once again it will come back to us. But this sound, the reflected sound and the original sound is going to be mix each other. So the reflected sound and the audible what we are speaking, that will be not clear at all. So both are different. When you're going to see the reflection of the sound and what we are hearing, both are not equivalent. So if you want to hear a clear sound, so the object and the source, this is the source and this is the object, so both are must be having certain distance. That distance we call it as the 17 meter. We know already the speed of the sound will be 340 meter per second. Okay, so when we would like to hear the echo, that means clear reflected sound, so it must be the source and the object must be minimum distance must be maintained about 17 meters. So here by using the calculation d is equal to Vt by 2, then we can find the value of distance. Why it is, we know the velocity is equal to distance by time. Here the source is there and here the object is there. Once the sound is coming out of the source and it reaching the object, and once again it will travel the same distance and come back to the source. That's why here it is d distance traveled and here also d distance traveled. So the total distance is 2d. And the total time taken is t. So that's why v is equal to 2d and d is equal to v by 2. By using the value of the speed of the sound, which is 340 meter per second, and we can have the echo in the time of 0.1 second. So we need the sound to hear very clearly, the reflected sound very clearly. We need about the time of 0.1 second. So the next time you stand near a cliff or large buildings, try shout and see if you can hear your own voice returning or not. Now let us discover one of the coolest applications of sound. How do ships measure ocean depth? Here the answer. Sonar, by using sonar. Sonar full form is sound navigation and ranging. So here the ships send a sound pulse, then it reflects from an object and return back. by using the formula D is equal to Vt by 2. They will calculate the depth of the ocean and the detection of the submarine. They actually find the time of the return of the reflected wave. Then let us come to the bats, which are mostly roam or come out from the caves at the night time. So bats use the technique, naturally we call it as the echolocation, while ships use sonar to navigate underwater. Sound does not just help us hear, it helps us see what our eyes cannot. Here the end for the part 1. So far we have uncovered some incredible secrets of sound. We learned how vibration creates sound waves, how energy travels from one particle to another particle, why thunder arrives late, and how echoes help us measuring distance. But our journey is so far from over. In part 2, we will explore even more fascinating mysteries. How human ears sound, why some sounds are musical while others are noise, resonance, and many real life applications that shape our modern world. Until then, listen carefully because sound physics is speaking to you through every sound around you. See you in the next part. Please subscribe and click on the bell icon. Thank you.